In the vast silence of eternity, endings are inevitable. Stars exhaust their fuel, dimming into cinders. Galaxies drift farther apart, like lanterns carried away by an endless tide. Even the mightiest black holes, once thought eternal, slowly evaporate, their gravity bleeding into the void. The universe, as it is known, is a story unraveling, page by page, toward silence. And yet, within silence, another possibility stirs. An ending does not always mean death. Sometimes it is a threshold. The cosmos may not fade into nothingness, but into a transformation, collapse, birthing, renewal, darkness, kindling a hidden flame, like a phoenix that rises from its own ashes. The universe may be a cycle, burning itself away only to begin again. Picture it not as a line, fixed and unidirectional, but as a breath. The inhale of creation, the exhale of destruction, or a heartbeat pulsing across unimaginable stretches of time. A spiral where each turn of existence is not a repetition, but an echo reshaped with every return. Here, philosophy and science converge in unease. If the universe can begin again, what then becomes of time itself? Do histories repeat exactly, with every atom, every life, every thought destined to return? Or does each rebirth carry novelty, creating new paths, new possibilities, forever? Branching into the unknown, the present cosmos glows faintly, like embers dwindling in a cosmic fireplace. But behind the veil of darkness waits something haunting, a spark not yet seen, a whisper of another universe, ready to awaken and begin everything again. Long before telescopes reached into the night sky, long before equations mapped the curvature of space-time, humanity looked upward and sensed a mystery. The heavens did not feel like a straight line, rushing endlessly forward. They seemed cyclical, like the seasons, like the tides, like the breath of living things. In myths carved onto stone and whispered into firelight, the first storytellers imagined the universe not as a singular beginning, but as a rhythm, birth, death, and renewal. In the ancient Vedic texts of India, the cosmos itself was said to breathe, one great cycle called a kalpa, stretched across billions of years, where the universe was born, flourished, dissolved, and then reborn again. Time, in this vision, was not a one-way arrow, but an eternal wheel. Hindu cosmology spoke of Brahma inhaling and exhaling worlds, a metaphor so hauntingly close to modern cosmological cycles that physicists today still remark on its uncanny resonance. In Greece, philosophers such as the Stoics pondered the notion of eternal recurrence. They imagined a cosmos that burned away in great conflagrations, only to be born again from its ashes, repeating its own history in an endless loop. For the Mayans, time was a spiral carved into stone calendars, an endless dance of destruction and creation. Norse sagas told of Ragnarok, the twilight of the gods, after which a new world would rise, green and fertile. To begin the story once again, these myths did not speak in scientific language, but they carried an intuition that existence might not end in silence, but circle back upon itself, that from destruction comes renewal, that every ending is also a beginning. Centuries later, as science took shape, time was given a new definition. Isaac Newton, in the 17th century, imagined time as absolute, an invisible stage upon which all events unfolded. Time flowed uniformly, like a river rushing endlessly in one direction. To Newton, the universe had no cycles. It was eternal, infinite, and unchanging in its framework. The laws of motion and gravity described objects within it, but time itself was indifferent, an absolute background that cared nothing for beginnings or ends. And yet, this conception of time was not to last. In the early 20th century, Albert Einstein rewrote the script. With general relativity, time was no longer absolute. It was interwoven with space, forming a pliable fabric called space-time. And this fabric was not fixed. It bent beneath the weight of matter, curved under the pressure of energy, and responded to the dynamics of the cosmos itself. Suddenly, time was not an indifferent river. It was a living landscape, shaped by the very objects it contained. Einstein's equations, elegant and profound, opened the door to possibilities Newton could never have imagined. Among them was the startling realization that the universe itself could not be static. In 1917, Einstein attempted to resist this conclusion. He introduced the cosmological constant, a term that allowed for a balanced eternal universe, neither expanding nor contracting. He called it his greatest blunder, for, in truth, his equations naturally suggested that the universe must evolve. It must change. It could expand or collapse, but it could not simply remain. It was the Russian mathematician Alexander Friedman, in 1922, who followed the logic to its conclusion. He found solutions to Einstein's equations that described a cosmos in motion, one that could begin in a singularity and expand outward, or collapse back upon itself, perhaps in a rhythm of oscillation, a universe that did not last forever in one state, but breathed in cycles of creation and destruction. A few years later, Georges Lemaitre, a Belgian priest and physicist, advanced the idea further. He spoke of a primeval atom, a singular point from which the universe began. This was the seed of what would later be called the Big Bang, the idea that our universe had a birth, a moment when time and space themselves emerged. But even in Lemaitre's vision lingered the haunting implication. If there was a beginning, could there not also be an end? And if an end, could another beginning follow? Then came Edwin Hubble. In 1929, peering through the great telescopes of Mount Wilson, he saw galaxies rushing away from one another. The universe was not static, as Newton once believed. It was expanding. This discovery transformed cosmology forever. If galaxies were moving apart now, logic demanded that in the past they must have been closer. Trace the motion backward far enough, and one arrives at a moment when all was compressed into a single origin, a beginning. This was scientific proof that the cosmos was not eternal in its present form. It had a birth, and if it had a birth, then perhaps, just perhaps, it could also be reborn by the mid-20th century. The Big Bang model emerged as the leading theory, yet it remained controversial until 1965, when Arno Penzias and Robert Wilson accidentally discovered a faint hiss of microwaves while calibrating a radio antenna. This was no ordinary noise. It was the fossil light of the early universe, stretched across the sky, the cosmic microwave background, a relic from the first moments after the Big Bang, still echoing today. It was confirmation that the universe had indeed begun in a singular event, but with confirmation came questions. If the universe began once, why not again? If space-time itself can emerge, why assume it must do so only once? Scientists began to speculate. Could the universe be cyclic, undergoing endless expansions and contractions? Could the Big Bang itself be the latest in a series of cosmic breaths, each universe giving rise to the next? The seeds of these questions were already planted in Friedman's oscillating solutions. Now they gained new urgency. The cosmic microwave background spoke of a beginning, but it also pointed to a gap. Between that first fireball and the galaxies we see today lies a veil of mystery, a place where the physics of singularities reign, where the known laws of science break down. In that silence lurks the possibility that beginnings and endings are illusions, that the universe may be far older, far stranger than even the Big Bang suggests. The discovery of expansion, of the microwave background, of relativity's pliable space-time, these were milestones. But each one carried within it a haunting echo. The universe is dynamic, unstable, perhaps even cyclical. If it began once, it could begin again. If it dies, perhaps it is not death at all, but the first breath of another age. Through myth, philosophy, and science, a thread emerges. From the wheel of Hindu cosmology to the singularities of Einstein. From Hubble's expanding galaxies to the fossil light discovered by Penzias and Wilson, the story points in one direction. The universe is not fixed. It changes, it evolves. It may collapse, and in collapse may lie the seed of renewal. This is the discovery phase of a mystery deeper than any other. Humanity has glimpsed its origins, but with every glimpse, a darker question follows. If the universe can begin, can it also begin again? The shock did not arrive with thunder, but with arithmetic. Numbers arranged into laws, whispered an ending. Not a final scream, but a long unspooling of heat into cold, of patterns into dust. Physics, the sober keeper of nature's ledger, looked into the future and found not drama, but depletion. It called this fate, heat death, the end, toward which all closed systems drift, where energy spreads thin, temperature differences vanish, and no more work can be done. The second law of thermodynamics is not a tyrant, only a statistician, yet its statistics rule the possible. Entropy increases, and with it the arrow of time points one way. The revelation was unsettling. If entropy must grow, then the universe must tire. Stars burn out, gas thins, black holes evaporate. Motion persists, but meaning fades. In such a cosmos, beginnings feel like brief exhalations and endings like an infinite inhale that never releases. The shock was not only existential, it was structural. Time itself, once imagined as a line indifferent to direction, suddenly acquired a preferred way to flow, past to future, order to disorder. If the universe could start over, how could it push against the one law that does not relent? The next jolt came from geometry. General relativity had transformed gravity from force into curvature, showing that matter and energy sculpt the lanes along which everything moves. If space-time itself can stretch, then the universe can evolve. It can begin and it can end. That was already a philosophical quake, but the data made it seismic. In 1929, Hubble's recession of galaxies announced expansion. In 1965, the cosmic microwave background confirmed a hot birth. Together they formed a chronology, a dense early fireball, a cooling plasma, atoms condensing, stars igniting. A timeline implies a boundary. The equations traced backward ran toward a singularity, not merely a place, but the breakdown of the very story the equations tell. A singularity is a confession. Relativity admits that its domain ends there. Quantum mechanics, asked to speak, loses its footing in the gravitational storm. If the universe starts at a singularity, Physics begins where physics fails. And if the universe must start over, does it pass again through the same unexplainable door? The shock was not that the universe had an origin. It was that the origin lies beyond explanation in current law. Then, a deeper astonishment, expansion, was not slowing. In the late 1990s, two teams measuring distant type Ia supernova found that the universe is accelerating. Space does not merely stretch, it stretches faster with time. Something called dark energy acts like a pressure embedded within the vacuum, driving galaxies apart. If it remains constant, distant futures grow lonely. If it strengthens, the cosmos may face stranger endings. A big rip where acceleration tears galaxies, stars, planets, even atoms from themselves. In each case, the direction is outward. A universe that starts over by collapsing, a big crunch, becomes hard to envision if dark energy wins. Yet, the very word dark signals ignorance. Dark energy is an effect without a known cause. The shock was doubled. Not only is the fate of everything altered by a component that cannot be seen, it also dominates the budget of existence. Ordinary matter, stars, gas, dust, bodies, is only a minor line item. The rest of the ledger reads, unknown, unknown. Dark matter sculpts galaxies. Dark energy sculpts expansion. The observed cosmos is a small island, and the islanders draft their future from tides they do not understand. How, then, can a resurgent universe be predicted if its present is already ruled by mysteries? Into this uncertainty stepped the most compact engines in nature, black holes. They concentrate gravity until escape is impossible. They are the places where time flows inward. Their existence was once controversial. Now it is televised in shadows. The Event Horizon Telescope revealed the silhouette of M87*, a ring of light, imprisoned by curvature. But the true shock hides not in the image, but in the paradox. Black holes swallow. Quantum theory insists that information is never lost. If a black hole evaporates by Hawking radiation and leaves no trace, where does the information go? If it is preserved, how? The information paradox is a reef on which both relativity and quantum mechanics scraped at. Here the question of a universe beginning again acquires teeth. If information is preserved in principle, then the universe carries a memory across its transformations. If it is not, then quantum law itself must bend. A reset might be possible, but what is reset, and what remains? A cosmos that starts over could be a universe that remembers in code too subtle to see. Or it could be a fresh coin toss, a new throw of laws from a deeper probability. The shock is to meaning. Recurrence can be either echo or reinvention. Our theories do not yet decide. Another tremor arose from the earliest moments after the Big Bang. The patterns in the microwave, background, tiny variations in temperature. Across the sky showed a strange smoothness and a specific spectrum of fluctuations. To explain them, cosmologists posited a brief, violent swelling, inflation, an exponential growth of space that ironed the observable universe flat, seeded quantum fluctuations into the scaffolding for galaxies, and solved puzzles of horizon and flatness in one gesture. But inflation itself is a theory of beginnings that implies further beginnings. In many models, it does not end everywhere at once. Instead, it stops locally and continues elsewhere, budding bubble universes. In this eternal inflation, starting over is not rare, it is the default. The multiverse becomes a landscape of beginnings. an orchard of big bangs. The shock is conceptual. If beginnings are abundant, then our universe is not the story, but a story. Against this horizon of plurality, entropy re-enters as a judge. If each new bubble starts with low entropy, where does the reset come from? How is the second law obeyed if the cosmic casino keeps dealing fresh hands? Some answers point to measures over infinite ensembles, others to deep statistical structures that make low entropy patches inevitable given enough space and time. But these are answers paid for with infinities, a currency easy to mint and hard to spend responsibly. The shock is methodological, future and past risk being explained by arguments that no experiment can touch. Meanwhile, laboratory physics whispered a more tangible dread. The vacuum may not be truly stable. The Higgs field, whose excitation gives mass to elementary particles, may sit in a metastable state, a local minimum of the potential energy, not the true floor. In that case, a quantum fluctuation could, in principle, trigger a vacuum decay. A bubble of lower energy reality expanding at nearly the speed of light, rewriting physics as it goes. No warning, no defense. Here, starting over becomes a catastrophe, not a cycle, a redefinition of what counts as a particle, a law, a constant. The shock is the intimacy of it. Rebirth could arrive not from cosmic collapse, but from a microscopic betrayal of the present vacuum, and still another disturbance, observations of supermassive black holes shining as quasars when the universe was less than 1 billion years old. There was not, by naive accounting, enough time for small seeds to grow so large. To reconcile, astrophysics entertained exotic beginnings, direct collapse black holes forming without stars, dense inflows, feeding rapid growth, mergers swarming in early halos. Each solution is a narrative of urgency, a cosmos in a hurry. The deeper implication is symmetrical to the central question. If the universe can accelerate its structures into being, perhaps it can accelerate its end, or its renewal, the shocks. Therefore, align like beads. Entropies, arrow, singularities, silence, dark energies, push, black holes, paradox, inflations, plurality, vacuums, fragility. Each bead reflects the same face, that of a universe whose origin and destiny lie at the edge of current law. Physics explains almost everything in between with astounding fidelity. It falters at the first, second, and the last. If the universe starts over, the start and the over are both places where our equations look back at us and say, not yet. This not yet is not defeat. It is a map. The increase of entropy tells where time points, but not whether time loops in space beyond. Sight. Relativity tells how geometry evolves, but not how to follow it through a singularity without tearing the page. Quantum mechanics tells how information lives, but not whether it can cross horizons unscathed. Each theory is a lantern. The shocks mark the fog ahead. The emotional register of these facts is difficult to ignore. The sciences that comfort with predictability also reveal abysses where prediction ends. A singularity is not a poetic flourish. It is an address where formulas yield infinity. A heat death is not a metaphor. It is a ledger that says, nothing left to spend. An accelerating expansion is not a philosophical fancy. It is a measured brightening and dimming of supernova light across billions of years. The shock is that the cosmos can be both legible and resistant, intimate and alien. If the universe starts again, what becomes of identity? If information is preserved in some holographic register of horizons, then the next cosmos could inherit statistical traces of this one, not memories in any human sense, but constraints, correlations, a grammar. If the vacuum decays, the new universe may write in a different alphabet altogether. If there is a bounce, instead of a bang, some quantum mechanism that averts infinite density and reverses collapse, then perhaps entropy resets via degrees of freedom hidden from ours, or funnels into dimensions we do not see. Each possibility is a different shock, recurrence with memory, recurrence without memory, transformation beyond translation. The most unsettling shock may be this: endings and beginnings are not opposites. In relativity, horizons, separate regions, without destroying either. In quantum theory, destruction can be a change of basis. The universe could start over not by erasing itself, but by re-expressing itself, a change in the code that keeps the story going under a new interpretation. The end of one solution to the equations might be the initial condition of another. Science stands, then, at a precipice it constructed honestly. It has measured the expansion, mapped the background, weighed the dark, imaged the shadow, and timed the waves. It has discovered that the universe is both more comprehensible and more provisional than anyone expected. The shocks are not failures. They are invitations, doors marked with paradox, beyond which the question waits with renewed urgency. If the universe starts over, what survives the crossing, law, memory, or only possibility? The shocks left a silence, but into that silence entered instruments. Questions that seemed destined for philosophy were handed to technology. The laboratory and the telescope became the new temples of origin. If the universe might begin again, then its fingerprints from the first beginning must linger, woven into radiation, matter, and structure. The task of science was to search for those remnants, as though the cosmos had left a diary in the margins of its expansion. The most delicate page of that diary is the cosmic microwave background, CMB. Discovered in 1965, it is the cooled afterglow of the Big Bang, stretched by expansion into microwaves, filling all of space with a uniform hiss. Yet the uniformity is not absolute. Satellites like COBE, WMAP, and most precisely Planck-mapped. Its tiny fluctuations, temperature differences of 1 part in 100,000. From those faint ripples emerged a revelation, the seeds of galaxies, the scaffolding of the cosmic web. The CMB is both fossil and prophecy, a snapshot of a young universe and a script for its later architecture. But cosmologists looked deeper, asking whether it carries scars of previous universes. Certain anomalies, the cold spot in the southern hemisphere, strange alignments called the axis of evil, have invited speculation. Could these be the bruises of collisions with earlier cycles, traces of a bounce, or echoes from eons past? Planck's data did not settle the debate, but it sharpened it. If the universe begins again, some argue, its past selves may have written across the sky in subtle, fading ink. Another frontier emerged in the idea of inflation, the rapid swelling, that likely occurred in the first fraction of a second. If true, inflation smoothed the cosmos, but also generated quantum fluctuations that later became galaxies. The hunt began for beam modes, a curling polarization pattern in the CMB that would reveal primordial gravitational waves, ripples from the inflationary storm. In 2014, the BICEP 2 experiment claimed detection, a possible glimpse of raw, but galactic dust dimmed the claim. The signal was not confirmed. Still, the search continues. If inflation is proven, the question returns: does it end once or endlessly? Many versions of inflation predict eternal budding, a multiverse. The search for BMODs is thus not only a search for early physics, but for the possibility that our universe is one cycle among many, one beginning in a garden of beginnings. Instruments on Earth also joined the effort. Radio telescopes, like LOFA, and preparations for the Square Kilometer Array (SKA), aim to listen for the 21-centimeter line of neutral hydrogen, stretched by cosmic expansion. This signal carries information from the Dark Ages, the time after the CMB, but before the first stars ignited. To detect it is to tune in to the silence before dawn. Yet even silence speaks. If the first stars formed earlier or differently than expected, the hydrogen's fingerprint will betray it. Detecting when and how the first lights reionized the universe may reveal whether cycles leave signatures in matter, not just in geometry. The fireflies of cosmic dawn could be lanterns for much older mysteries. On still larger scales, astronomers map the cosmic web itself, filaments and voids spanning billions of light years. Surveys like SDSS, DESI, and future projects like Euclid reveal a universe arranged not randomly, but in patterns consistent with early quantum fluctuations. Yet hidden in that arrangement might be clues to deeper regularities. If cycles exist, if universes bounce, then the statistical distribution of galaxies could carry subtle imprints of previous eons. Cosmologists test models against these maps, comparing simulations of bouncing cosmologies with the structures we observe. So far, no decisive echo has appeared, but the effort reveals the ambition to read eternity from the distribution of galaxies, to hear the universe's past lives in the chords of its present structure. The theoretical laboratory complements the observational. Mathematicians and physicists explore models that replace singularities with bridges. Bouncing cosmologies imagine the Big Bang as a rebound from a prior contraction, removing the singularity and allowing history to flow through the eye of the needle. Loop quantum cosmology, derived from loop quantum gravity, predicts that space itself is quantized, made of discrete loops. In such models, when densities grow extreme, quantum repulsion halts collapse, and a bounce ensues. The universe starts again, not from nothing, but from transformation. Instead of erasure, renewal. If true, this suggests that our cosmos carries memory, not invisible relics, but in the deep fabric of quantum geometry. Another speculative approach comes from Roger Penrose's conformal cyclic cosmology, CCC. Penrose proposes that as the universe expands and black holes evaporate, scale loses meaning. The infinite, empty future of one universe becomes mathematically identical to the dense beginning of another. Eons follow eons, each connected not by collapse, but by a conformal transformation. Penrose and collaborators even suggested that certain concentric circles in the CMB could be evidence of supermassive black hole collisions from a previous eon. Though controversial, the proposal exemplifies the deeper investigation to find continuity where endings appear absolute. In laboratories closer to home, physicists interrogate the Higgs field and the possibility of vacuum instability. Particle accelerators like the Large Hadron Collider, LHC, measure the Higgs boson's mass and self-coupling, trying to determine whether our vacuum is stable or metastable. If metastable, then quantum tunneling could someday trigger vacuum decay, a reset at the most intimate level of reality. Here, the laboratory and the cosmos meet. What happens in a particle accelerator refines what could happen to the universe itself. The smallest experiment becomes an inquiry into the largest. Observations of stars add another layer of archaeology. Astronomers study the oldest, most metal-poor stars in the Milky Way's halo, searching for chemical signatures of the first generation of stars. These population 3 stars are gone, but their descendants bear fingerprints of the elements forged in their cores. By reconstructing that history, scientists probe the early conditions of cosmic dawn and indirectly the nature of beginnings. If universes restart, then the laws that governed the first stars could govern again or shift in subtle ways. Each abundance pattern in a distant, ancient star becomes a probe into the repeatability of creation. The deeper investigation also extended to black holes themselves. Far from being dead ends, they became laboratories. LILO's detection of gravitational waves in 2015 confirmed ripples in space-time predicted a century before. Each merger is not only a collision, but an experiment in strong gravity where quantum corrections might someday be visible. Some speculate that signatures in gravitational waves could reveal deviations from general relativity, hints of quantum gravity. If those deviations suggest a way around singularities, they would point directly to mechanisms for cosmic rebirth. Black holes, which seem to seal off futures, may instead be the first cracks in a door toward renewal. Philosophically, the deeper investigation complicates the meaning of beginnings. If inflation is eternal, then beginning is local. If bounces replace singularities, then beginning is transition. If vacuum decay looms, then beginning is catastrophe. If Penrose is right, then beginning is scale. None of these possibilities grants the comfort of a single origin. Each suggests that what we call a beginning is only one part of a longer process. Emotionally, the investigation deepens the unease first brought by the shocks. Science has traced the universe back 13.8 billion years, mapped its radiation, catalogued its galaxies, and simulated its structures. Yet every advance reveals that the question, what happens if the universe starts over, is not speculative ornament, but embedded in the equations. Relativity invites collapse. Quantum fields invite tunneling. Thermodynamics invites renewal. The laboratory, the telescope, the computer, all converge on a strange possibility. Beginnings are not rare, but structural, and so the search continues. Future missions, James, Webb, Lisa, Euclid, SKA, extend the eyes and ears of humanity deeper into the early cosmos. Supercomputers evolve models of inflation, bounce, and decay. Particle colliders probe the stability of the vacuum. Each effort sharpens the contours of the question. The deeper investigation does not resolve the mystery. Instead, it transforms it. The universe may start over, but whether as echo, as reinvention, or as something beyond either remains unseen. The diary of beginnings is vast. We read its entries in photons, in gravitational waves, in elements. In equations, some lines are clear, others smudged, others missing altogether. Yet the act of reading changes the reader. Humanity's pursuit of this mystery is not only about predicting the cosmos, but about situating itself within cycles beyond measure. The deeper investigation reveals a universe that is not linear, not static, not final. It is a universe whose story may not be one volume, but a library, and we, for now, are somewhere in the middle of a chapter whose beginning is still being written, and whose ending may become the seed of another tale. The deeper investigation sharpened the outlines of a possible rebirth, but as the picture grew clearer, so too did its shadows. The mystery did not dissolve. It multiplied. Each discovery seemed to open a corridor into stranger terrain, where the end of the universe was not a quiet fading but a violent metamorphosis, where beginnings were born from catastrophes. The questions became heavier, the possibilities more haunting. What if the universe is not only capable of beginning again, but destined to? The first great escalation arrived with the discovery of dark energy. For decades, cosmologists had expected that gravity, universal and attractive, would slow expansion. In some scenarios, it might even reverse it, leading to a big crunch where the cosmos collapsed into itself, setting the stage for another bang. But in the late 1990s, measurements of distant Type Ia supernova revealed something shocking. Expansion was not slowing, but accelerating. A hidden energy, uniform and repulsive, was woven into space-time. Named dark energy, it acts as an invisible hand pushing galaxies apart faster and faster. If its strength remains constant, the universe will never collapse. Instead, it will drift toward eternal isolation, a cold and dark horizon. But if dark energy changes with time, if it grows stronger, then escalation follows, a big rip, where galaxies, stars, planets, and even atoms are torn apart. Such an ending leaves little room for rebirth, and yet physicists cannot ignore the possibility that dark energy may be dynamic, a phase that could reverse, transforming expansion into contraction. The fate of the universe, and whether it restarts, depends on the most elusive property in modern physics. Another escalation emerges from the concept of vacuum instability. Quantum field theory suggests that our universe's vacuum the background. Energy level of space may not be the true lowest state. Instead, it could be a false vacuum, metastable, like a ball resting in a shallow valley when a deeper one exists nearby. If so, quantum tunneling could one day trigger a collapse, with a bubble of lower energy vacuum expanding at nearly the speed of light, rewriting the laws of physics as it spreads. Particles, forces, even dimensions could change. For our cosmos, this would be an annihilation. For reality, it might be a rebirth, the ignition of a new universe governed by different rules. The chilling escalation is that such a collapse could occur without warning, and there would be no way to detect it before it arrives. The same equations that give stability to the present whisper of catastrophe in the future. Some visions are stranger still. If dark energy strengthens endlessly, the universe may end not with collapse, but with dismemberment. The big rip, galaxies would dissolve, stars torn apart, planets shredded, molecules unbound. In the final moments, even nuclei and space-time itself would rupture. This scenario is terrifying in its completeness. Yet some cosmologists speculate that the wreckage could reset, that from the torn fabric might arise new quantum fluctuations, seeds of another universe, not by compression but by dissolution, a cycle of destruction, not of collapse, where every end is a rift that births another cosmos. Into this landscape of endings came anomalies in the cosmic microwave background, CMB. Already mapped in exquisite detail, it remains the most reliable record of the early cosmos. Yet in its smoothness lie peculiar features. A vast cold spot, colder and larger than standard cosmology predicts. Alignments of temperature fluctuations dubbed the axis of evil. Hemispherical asymmetries that resist simple explanation. Some scientists argue these are statistical flukes, accidents of observation. but others, including Roger Penrose, suggest they may be signatures of prior cycles, evidence of collisions, events, or structures from before our own Big Bang. If true, then the CMB is not just a fossil of one beginning, but a palimpsest of many. The escalation is philosophical as much as physical. If the universe restarts, then our cosmos may already carry whispers of its predecessors. Embedded in radiation we mistake for noise. Black holes, once thought of as mere endpoints, add further tension. Observations reveal supermassive black holes in galaxies less than 1 billion years old, objects billions of solar masses, formed too quickly for standard models. Their existence suggests unknown processes, perhaps collapses, more violent, or inheritance from prior cycles. Some speculative models even propose that each black hole births a new universe, its singularity a seed of expansion on the other side. In this view, universes beget universes, and ours could be the child of collapse in a deeper reality. If so, then beginnings and endings intertwine, each black hole a womb, each universe a lineage. The cosmic web itself complicates the story. Galaxies do not float in isolation, but thread into filaments, surrounding immense voids. This structure, observed by surveys across billions of light years, resembles a neural network, filaments of matter glowing like synapses of an unimaginable brain. Gravity sculpts these forms, but dark energy tugs them apart. The web is dynamic, an evolving structure that may carry memory of earlier cycles. If universes restart, then the web we see may be one version of a pattern repeated across eons. And yet, the pattern's persistence deepens the mystery. Why does matter always assemble in these webs? Why do the same shapes echo across scales? And perhaps across cycles, beneath all of these escalations, lies the unification crisis. General relativity describes gravity with extraordinary success, but it breaks at singularities. Quantum mechanics governs particles and fields with equal mastery, but cannot reconcile with gravity's continuum. Attempts to unify them, string theory, loop, quantum gravity, holography, each promise resolution, but none is complete. This fracture is not trivial. It is the crack at the foundation of physics, the place where beginnings and endings slip through theory's grasp. If the universe starts again, it will pass through precisely this gap, the domain where no theory yet holds. The escalation, then, is existential for science itself. The universe demands an answer that physics does not yet possess. Philosophically, the deepening mystery unsettles human meaning. If the cosmos is cyclic, are we destined to return, endlessly repeating lives we cannot remember? If every universe is new, then everything we are is temporary, erased at each reset. Both possibilities are heavy. Eternal recurrence challenges the uniqueness of history. Eternal novelty erases continuity. In either case, humanity's story is both smaller and larger than imagined, small against the immensity of cycles, yet large as a fleeting expression of reality itself. Emotionally, the escalation evokes awe and dread together. The universe may not fade into silence, but convulse into renewal. It may not end once, but endlessly. Its restarts may be hidden in microwave radiation, in gravitational waves, in anomalies we have not yet explained. The very laws that grant predictability, relativity, quantum theory, thermodynamics, suggest scenarios where predictability breaks, where beginning and end fold into one. The mystery deepens with every step. Expansion accelerates, but its fate is unknown. Black holes swallow matter, but may seed new universes. Radiation whispers anomalies, but no certainty follows. The cosmos resists closure, refusing to offer a final narrative. Instead, it opens into escalation, into darker, stranger, more vertiginous possibilities. The haunting possibility remains: if the universe starts over, we may never know whether it repeats us, erases us, or transforms us into something beyond. Recognition, our place in this cycle, is not guaranteed. Perhaps nothing carries forward, perhaps everything does. The deeper we peer, the more the universe seems unwilling to surrender its secret. When science reaches the edge of data, it turns to theory. And when theory finds itself in the company of paradox, it opens the gates of speculation. The question of what happens if the universe starts over is not confined to one model or one vision. It is a crossroads where cosmology, quantum physics, and philosophy meet. Each framework offers its own narrative, some grounded in equations, others woven with metaphors of geometry, symmetry, or hidden dimensions. None are certain, but all are attempts to peer beyond the veil of the singularity into the unknown territory, where endings may transform into beginnings. The most intuitive and widely discussed is the Big Bounce. In this picture, the universe is not a one-time event, but part of an eternal oscillation. Expansion carries matter outward until gravity, entropy, or some hidden mechanism reverses the trend. Then comes contraction, galaxies drawn back together, space-time curving inward, stars and planets erased into a furnace of collapse. At the point of highest density, instead of a singularity, the universe rebounds. Expansion follows contraction. Bang follows crunch, each cycle birthing a new cosmos. This idea has roots in Alexander Friedman's 1920 solutions to Einstein's equations, later refined with modern tools of quantum cosmology. The bounce removes the need for a beginning ex nihilo. Instead, it frames existence as a rhythm, a heartbeat echoing across eternity. But even here, uncertainty lingers. Would each cycle repeat identically, or would quantum randomness paint each new cosmos in a slightly altered design? Another bold vision is the ekpyrotic universe, born from string theory and the mathematics of higher dimensions. In this model, our cosmos is not alone, but rests upon a three-dimensional brain, a sheet floating in a high bulk. Another brain exists parallel to ours, and from time to time, these brains collide. Each collision ignites what we perceive as a Big Bang. Our universe, then, is one pulse in a grand sequence of brain interactions. The cycles here are not expansions and contractions of one cosmos, but encounters between neighboring realities. Such a framework offers elegant solutions to certain cosmological puzzles, such as the smoothness of the early universe. But it comes at a cost. It demands unseen dimensions and physics far beyond direct observation. Yet, if the cosmos starts, again through brain collisions, our entire existence may be a side effect of universes brushing against each other in the dark. In contrast, Roger Penrose's conformal cyclic cosmology, CCC, envisions time not as an oscillation, but as a transformation of scale. According to general relativity, black holes evaporate over inconceivable timescales through Hawking radiation, leaving behind a universe devoid of mass, only radiation. As the last particles decay, the distinction between large and small, between seconds and centuries, dissolves. Scale becomes meaningless, and in this state, the geometry of the universe can be mathematically reinterpreted as the beginning of a new Big Bang. The end of one eon becomes the birth of another. Penrose has even claimed possible evidence, concentric circles in the CMB that may record gravitational ripples from black hole mergers of a prior eon. If correct, CCC implies that universes are strung together like pearls, not by collapse or collision, but by the erasure of scale. Each cycle is both an ending and a beginning, stitched seamlessly across infinite time. Another speculative horizon lies in the string theory landscape, where reality is not a single cosmos, but a vast multiverse of possible universes, each with its own physical constants, laws, and dimensions. Our Big Bang may have been a quantum fluctuation within this landscape, a bubble nucleating in an endless foam of possibility. If so, then starting over is not a repetition, but a branching. A new universe is not this one reborn, but a cousin, with altered parameters, a cosmos where stars burn differently, or where chemistry forbids life altogether. In this view, universes do not so much restart as proliferate, endlessly budding from the fertile soil of quantum spacetime. The unsettling implication is that beginnings are trivial, scattered everywhere, while our own universe's history is just one among an infinity of others. Closer to the marriage of quantum mechanics and cosmology lies loop quantum cosmology. Here, space-time itself is quantized into finite units, woven from loops of geometry. When density reaches the Planck scale, quantum gravity repels collapse, forbidding a singularity. Instead of infinite compression, a bounce occurs, a quantum spring that forces expansion. This model has the advantage of precise mathematics and testable predictions, such as potential imprints in the CMB. If correct, the universe could indeed restart endlessly, with each Big Bang the consequence of quantum geometry refusing annihilation. Unlike the philosophical abstractions of CCC, or the speculative brain collisions of ekpyrotic theory, loop quantum cosmology is grounded in an attempt to calculate, to measure, to connect directly with physics. More speculative still is the scenario of vacuum decay. If our universe resides in a false vacuum, its collapse would not merely end our cosmos, but ignite a new one. The bubble of true vacuum would expand, erasing old structures and reshaping constants, laws, and particles. To us, this is annihilation. To the universe, it may be renewal. Such a transition would be the most radical form of restarting, not repetition, not bounce, but metamorphosis into something entirely unfamiliar. Within this framework, universes may continuously overwrite themselves, each collapse producing a radically different successor. Philosophy shadows these models as much as physics. Nietzsche's eternal recurrence suggested that all events may return infinitely, each life lived again in exact repetition. Modern cosmology cannot affirm such precision, yet it resonates with the big bounce, with the haunting possibility that cycles may preserve echoes. Whitehead's process philosophy, where reality is not substance but event, harmonizes with theories that emphasize transitions over states. The metaphor of the spiral recurs, time not as a line, not as a circle, but as a curve revisiting it. Path without duplication. Each rebirth is neither identical nor wholly novel, but a variation upon themes. What unites these theories is their confrontation with the singularity. In Einstein's equations, the singularity is the point where mathematics breaks, where density becomes infinite, where time itself dissolves. To start over, the universe must pass through or around this limit. Every speculative model is, at heart, a strategy to evade singularity. The big bounce replaces it with compression and rebound. CCC erases scale until singularity is meaningless. String theory disperses it into higher dimensional interactions. Loop quantum cosmology forbids it outright through quantization. Vacuum decay replaces it with phase transition. The singularity is the wall. Speculation is the attempt to find the hidden door. Yet each theory faces limits. Observations of dark energy suggest eternal expansion, incompatible with simple cyclic models. String landscapes predict universes we cannot see. CCC depends on subtle patterns in the CMB that remain controversial. Loop quantum cosmology remains mathematically elegant but empirically elusive. Vacuum decay is consistent with particle physics but unverifiable until it happens. Each theory reaches toward truth, but none hold it fully, and so speculation becomes not only scientific but existential. If the universe starts again, do we? Is life inevitable, seeded each time by the same physics? Or is our existence a cosmic accident, one never to be repeated? If laws shift in each cycle, then humanity may be a fleeting phenomenon, erased not just by time but by the transformation of reality itself. And if recurrence is exact, then every word, every breath, every grief and joy will return endlessly. A loop without escape. The theories differ in their mathematics, but they share a haunting commonality. All suggest that the universe is not singular, not final, not one. Instead, it is layered, sequential, or proliferating. Its story is never complete. Each end is a transition. Each silence holds the seed of another beginning. The universe may collapse, collide, evaporate, or decay, but in every model, destruction is not the last word. It is a prelude, a transformation, a threshold. Whether by bounce, by brain, by eon, or by bubble, the cosmos may never allow itself to truly end. To move beyond speculation, science must turn its gaze to instruments, machines, telescopes, and detectors that allow humanity to reach across time, to interrogate the universe itself for traces of its hidden cycles. If the cosmos is capable of beginning again, then its earlier echoes may linger in the faintest signals, waiting to be revealed. Each observation, each experiment, becomes a question whispered to reality. Did this all happen before, and will it happen again? The James Webb Space Telescope, JWST, is at the vanguard of this search. With its golden mirrors unfolding in space, it is designed to see the faintest galaxies from the universe's dawn. By peering back more than 13 billion years, JWST captures light stretched into the infrared by cosmic expansion. Already, its instruments have revealed galaxies forming astonishingly early structures, appearing within the first few 100 million years, earlier than expected. Such discoveries ripple into theories of rebirth. If galaxies could assemble so quickly, then perhaps the conditions for star formation were inherited from processes predating our Big Bang, or shaped by physics that hints at prior cycles. JWST's data becomes a test for models like the Big Bounce or Penrose's CCC, seeking whether anomalies in early structure betray the fingerprints of an older cosmos. But JWST is only one lens. Other eyes search with different tools. 21-centimeter radio astronomy offers perhaps the purest key to the cosmic dark ages, the time between the Big Bang and the first stars. The hydrogen line at 21 centimeters provides a way to map neutral hydrogen. Across vast stretches of time, Arrays like LAFRA and the upcoming Square Kilometre Array SCAR aim to detect the faint absorption and emission signatures of hydrogen disturbed during cosmic dawn. If cycles exist, they might leave statistical imprints in this hydrogen background, subtle deviations in distribution, or anomalies inconsistent with a one-time beginning. These radio whispers may carry the oldest surviving memory of a universe. Preparing to start again on another frontier lie gravitational wave observatories. With the first detection in 2015, LIGO opened a new sense, the ability to hear space-time itself. Every black hole merger, every neutron-star collision sends ripples across the cosmos. But beyond these violent events may exist signals from the very birth of the universe, primordial gravitational waves. Unlike light, these waves could pass unscattered through the early plasma, preserving information from fractions of a second after the Big Bang. Instruments like LISA, the space-based laser interferometer space antenna, planned for the 2030s, may one day detect these ancient vibrations. If found, they could distinguish between inflationary beginnings, bouncing cosmologies, or cyclic eons. Gravitational waves may be the fossils of previous universes, still trembling faintly in the geometry of space-time. Particle physics, too, plays its role. The Large Hadron Collider LHC probes the Higgs field, the mechanism that endows particles with mass. Whether our universe is stable or precariously balanced in a false vacuum depends on the properties of this field. Current measurements suggest metastability. The universe may rest in a high-energy valley, with the possibility of collapsing into a deeper state. If true, then vacuum decay could be the mechanism by which universes end and restart. Future colliders, such as the Future Circular Collider (FCC), aim to measure the Higgs with greater precision, testing whether the fabric of our cosmos is eternal or fragile. In the smallest collisions, physicists search for answers to the largest of questions: whether existence itself can reset. Cosmic cartographers work on another scale entirely. Euclid and the Vera Rubin Observatory map galaxies and dark matter across billions of light-years by measuring how structures form and how light bends around invisible masses. These surveys reveal the influence of dark energy and gravity across time. If cosmic acceleration shifts, if dark energy evolves, then the universe's fate may differ from present expectations. A weakening or reversal could one day halt expansion, triggering collapse. A prerequisite for a bounce, a strengthening, could drive a big rip. Either scenario informs the question of renewal. The maps these observatories create are not only records of space, but predictions of destiny. Some tests unfold in more speculative territory. Chemical archaeology studies the oldest stars in our own galaxy, ancient metal-poor stars preserved. In the Milky Way's halo, these stars contain chemical signatures of the first supernova, hints of the earliest moments of nucleosynthesis. If the patterns deviate from expected predictions, they may point toward physics shaped by prior cycles or altered initial conditions. The ashes of the first stars may carry, however faintly, the memory of beginnings older than our own. Supercomputers also serve as telescopes of another kind. By simulating universes under different assumptions, bouncing, inflating, cycling, they allow scientists to predict what signatures might appear in observable data. These simulations act as rehearsals for cosmic rebirths, tracing whether structures, radiation, or gravitational waves would differ in a cyclic cosmos compared to a singular one. In this sense, computation becomes a form of observation, a way to peer into possibilities not yet accessible to instruments. Philosophically, the tools themselves embody the paradox of the question. Human civilization, fragile and brief, builds instruments spanning continents, orbiting the Earth, listening across galaxies, all to catch echoes billions of years old. Telescopes stare into the past. Colliders recreate fractions of a second after the Big Bang. Detectors listen for whispers, older than stars. The pursuit of whether the universe restarts becomes itself a cycle. Observation leading to theory, theory guiding new observation, endlessly repeating. Future projects extend this ambition further. Proposals for telescopes like Lavoir and the Origins Space Telescope aim to peer deeper into the early infrared universe, beyond even JWST's reach. These observatories would attempt to see galaxies at redshifts where cosmic dawn first broke, narrowing the gap between data and the beginning. Meanwhile, gravitational wave astronomy looks ahead to detectors capable of mapping not just mergers, but the cosmic background itself, turning space-time into a screen upon which prior universes might have written their signatures. In parallel, mathematicians and theorists search for equations uniting general relativity with quantum mechanics. If such a theory emerges, whether through string theory, loop quantum gravity, or something yet unimagined, it may allow precise predictions of what happens at singularities. Only then can science state, with more than metaphor, what it means for a universe to begin again. For now, the singularity remains the blind spot of physics, the wall against which all equations collapse. But the tools being built aim in their own way to see beyond that wall. And perhaps the boldest speculation, could humanity one day simulate an entire universe? With advances in quantum computing, some theorists suggest that future machines might model not just particles or stars, but the full dynamics of space-time. If achieved, such simulations could allow experiments with rebirth, running cycles of universes in silico, testing whether patterns recur. The simulation would not be a universe itself, but it could offer the closest mirror we have, a rehearsal for creation. The tools of science are imperfect, each with limitations, each straining against distance, faintness, or the noise of Earth. Yet together they weave a net across scales, from the quantum to the cosmic. Through this net may fall evidence, however slight, of whether beginnings are unique or endless, whether time flows once or spirals forever, whether the embers of our universe are final, or whether beyond them waits another spark. Instruments cannot yet answer definitively, but every detection of a distant galaxy, a gravitational wave, a faint chemical trace adds a piece to the mosaic. The question of cosmic renewal remains unsolved, but the search itself transforms the silence into inquiry. Science reaches into the abyss not only for data but for meaning, using glass, metal, and mathematics as its bridge. And so the tools continue their work, listening, watching, measuring, simulating. Each device is an extension of human wonder, probing whether the universe, in its vastness, carries within it the seeds of its own rebirth. In the silence of thought, the question lingers. What does it mean if the universe can begin again? The answer is not only scientific, but existential. It touches not only the stars, but the human spirit itself. The cosmos, in its vast expanse, has always been a mirror. When humanity asks whether the universe can restart, it is also asking whether life itself can be renewed, whether endings are truly final, or whether each loss carries within it the seed of return. The cycles imagined by science are reflected in the cycles of existence, birth and death, decay and renewal, memory and forgetting. The possibility of a reborn universe becomes more than cosmology. It becomes a metaphor for the condition of all living things. If the Big Bang was not unique, then nothing is singular. Our present universe is one verse in a larger song, one breath in an eternal rhythm. Penrose's conformal cyclic cosmology suggests that eons pass, each leaving faint traces on the next. In that vision, universes are not separate but linked, each whispering into the silence of the one to follow. The idea resonates with ancient myths, Hindu cosmologies of endless creation and dissolution, the Norse Ragnarok, the Mayan worlds rebuilt. Science, through its equations, touches once more the intuitions of old, that nothing is ever entirely lost. Yet this thought carries both comfort and unease. If everything begins again, then perhaps even this moment will return. Every decision, every sorrow, every triumph, repeating across countless cycles. Nietzsche's vision of eternal recurrence transforms into physics, the possibility that the spiral of time revisits its own steps. But is such recurrence a prison, where history endlessly repeats, or a liberation, where each cycle creates novelty? From old foundations, the answer is unknown, and perhaps unknowable. There is also humility in the thought of cosmic renewal. Human lives, nations, even civilizations feel vast on their own scales, but against the weight of universes, they are fragile sparks. If cosmoses are born and die, then humanity itself may be but one brief flicker in an endless procession. Yet even fragility has meaning. To live, even once, in one cycle of the universe is to share in something greater than eternity, the experience of existence itself. Science approaches these questions with caution. Instruments measure, equations predict, data accumulates. Yet beneath the rigor lies wonder. For the scientist, as for the poet, the possibility of universes beginning again is not just a hypothesis, but a meditation. It forces a confrontation with the limits of knowledge, the singularity where relativity fails, the quantum foam where certainty dissolves. In those limits resides the recognition that the deepest truths may always remain veiled, not out of hostility, but because they lie beyond the horizon of comprehension. Still, humanity seeks. Each observation of galaxies at cosmic dawn, each ripple of gravitational waves, each whisper of ancient hydrogen is a gesture toward understanding. The pursuit itself may be the point. Whether the universe restarts or not, the act of asking binds humanity to the cosmos. In the search for beginnings, humanity discovers itself, and so the closing reflection turns inward. If the universe restarts, then the matter of human bodies, the iron in blood, the calcium in bones, will one day be scattered and reshaped, perhaps into stars, perhaps into new worlds, perhaps into new beings capable of asking once more what it all means. In this sense, renewal is not speculation but fact. Humans are already made of the ashes of stars, already the continuation of cycles far older than Earth. The cosmos has begun again within each breath. But what of memory? What of identity? If universes restart, does consciousness return, or is it forever new? Physics offers no answer. The equations describe matter, energy, and space-time, but not the essence of awareness. Yet the question lingers, in an eternal sequence. Could the pattern of thought, the feeling of being alive, recur as surely as galaxies and atoms? Or is each spark of consciousness unrepeatable, unique against the infinite canvas? Here science, meets silence, and philosophy alone dares to imagine. The reflection deepens further. If beginnings and endings are illusions, if the universe flows as a river without true start or finish, then meaning itself shifts. Permanence ceases to be the measure of value. Instead, transience becomes sacred. The beauty of a star lies not in its endlessness, but in its brief light. The value of a life lies not in recurrence, but in the singularity of the moment lived. Even if universes restart, even if cycles repeat, each moment remains absolute in its own time. This perspective does not diminish wonder, it amplifies it. To imagine universes rising and falling is to see existence as a vast spiral, with humanity as a single step upon its curve. Whether repeated or not, the step matters. The spiral would not be complete without it. And so, the closing meditation rests on paradox. The universe may restart endlessly, and yet each restart may be wholly new. The cosmos may recycle itself, but the path it takes could always differ. Cycles may contain echoes, but never perfect repetition. In this view, renewal is not stagnation, but creativity. The universe, like an artist, paints upon the same canvas, but with different strokes each time. The imagery returns one last time. The cosmos as a breath, inhaling and exhaling across eternity. The cosmos as a heartbeat, pulsing, with beginnings disguised as endings. The cosmos as fire, burning, extinguishing, and reigniting from its own embers. Each metaphor circles back to the same truth. The question of renewal is as much about meaning as mechanics. Perhaps, in the end, the ultimate secret is this: the universe does not begin, and it does not end. It transforms. What we call a beginning is the continuation of what came before. What we call an ending is the seed of what follows. To ask whether the universe starts over is to recognize that it never ceased. The final image lingers, stars fading into darkness, galaxies dissolving into silence, black holes evaporating into whispers of light. Then, from that silence, a new spark, a new expansion, a new universe unfolding its wings. Whether it repeats or reinvents, whether it remembers or forgets, the cycle continues. Humanity may never see it, but it is enough to know. Existence itself refuses to be still. The question remains unanswered yet eternal. What happens if the universe starts over? Perhaps it already has. Perhaps it always will.